Now we'll move on to the dynamic programming. Dynamic programming is another way of solving the algorithms. The general method of this dynamic programming depends on the principle of optimality. Make note of this. You are supposed to follow the principle of optimality. The dynamic programming design method can be used when the solution to a problem can be viewed as result of sequence of decisions. The essential difference between the greedy method and dynamic programming is that in greedy method only one decision is ever generated. That means whatever the first step you do, that is nowhere related with the second step. But for every step in greedy algorithm, you will check for whether it is an optimal solution or not. This is the way you will do it in the greedy algorithms. Where in case of dynamic programming, the first step will be compared with the second step. Like that, second step will be compared with the third step. That means whenever you are doing third step, you will compare with the second step. And if you find a better solution than the previous step, then you will accept the third step, next step, and you will proceed further. Whenever you are doing the next to next step, you will check for the solution with the previous steps. So this is what the thing of principle of optimality. The dynamic programming design method can be used when a solution to a problem can be viewed as the result of sequence of decisions. The essential difference between the greedy method and dynamic programming is that in greedy method only one decision is ever generated. Always you will check for the best decision for every step. But the next step is not depending upon the previous step, or it won't take any lessons from the previous step and will go further. In dynamic programming, many decision sequences may be generated. However, sequence containing suboptimal subsequences cannot be optimal if the principle of optimality holds, and so will be generated. So will not be generated. Let us see the principle of optimality. The principle of optimality states that an optimal sequence of decisions has the priority has the property that whatever the initial state and decisions are, the remaining decisions must constitute an optimal decision statement with regard to the state resulting from the first decision. That means whenever you are doing the second step, it should be somewhat better than the previous step. This is what the principle of optimality. The same principle of optimality we might have seen in our philosophical talk with our elders. Philosophical talk in the sense a motivation talk or motivational thing in our home, from elders. That, for example, you might have studied well for your 10th class exams, and you expected that a 90% result you will get, but you got 85% result. So you may be in depression, but your elders may say that, okay, whatever may be happened is happened. Okay, don't worry about this. Okay, next you are supposed to do plus two. Okay, in plus two you achieve 90%. Okay, then in plus two you may thought of, okay, you have very struggled a lot, and you thought that you may get around 95% of marks, but unfortunately you got 90% of marks. But you may be depressed at the time, but your elders may say that, okay, leave it, it's over, it's gone is gone, happened is happened. But you have improved from the previous state, okay, 85% to 90%, from 10th class to the plus two. Okay, now you think of engineering. Of course, in engineering you never get more than 90%. It is very difficult to get it. Okay, however, assume that you have targeted for 95%. Okay, but you got only 65%. then the principle of optimality never holds. So always the principle of optimality is like this. Whatever is the initial decision, initial state may be, the next states must be better than the previous state. Then it is what the previous it is the principle of optimality. So there is a possible there may exist several possible solutions, but you choose a solution in such a way that the the solution that you choose, whatever the result you get, should be better than the previous state. Okay, that means if you look at a graph, if you place a career graph, always in 10th class you may be having a higher marks. Okay, plus 2 you may be having a little bit higher, but in engineering it may fall down. So here the principle of optimality doesn't hold. But if you get more than the previous stage, then it is said to be principle of optimality. That means you have achieved better marks than the previous degrees. So this is what the principle of optimality is. But in case of greedy algorithms, this principle of optimality will not be considered. In greedy algorithm, every level is every level only. That's all. Okay, you got better result at the 10th. Okay, it's fine. Okay, it's no way related with the second one. Okay, no way related with no comparison with the next stages. So this is what the slight difference between the greedy method and the dynamic programming. So dynamic programming, please remember dynamic programming based on the principle of optimality. Principle of optimality means whatever is the initial state it may be, the next states must be better than the previous state. That is what the principle of optimality is. So one example of this dynamic programming is all pairs shortest path algorithms. So single source shortest path algorithm that can be solved using greedy method that we have seen previously in the greedy method, greedy algorithms. Where in case of dynamic programming, this all pair shortest path algorithm is one best example with which we can solve. That means whenever there exist several possible paths from every pair to every pair, but whatever the initial path it may be, but the next path that you choose must be better than the previous path. That is what the principle of optimality that will hold in this all pairs shortest path algorithm. So let g is equal to v comma e be the directed graph with n vertices. Let cost be a cost adjacent matrix for g such that cost of I comma j is equal to 0, where I lies between 1 to n. Then cost of I comma j is the length of the edge, that is the edge weight that what we have placed. If I comma j is belong to edge and cost of I comma j is equal to infinity if I is not equal to j. That means if you are referring to the self thing or self vertex, then the cost of I comma j where I is not equal to j and is infinity, and I is equal to j is not equal to edge of g. So this is what the thing. That means if there exists no path between, if there exists no path, or if you are referring to the self, then it is you are supposed to replace it with the infinity. All pair shortest path determine a matrix A such that A of I comma j is the length of a shortest path from I to j. So here a matrix A can be obtained by solving an single source problems using algorithm shortest path. So whenever you have this adjacency matrix, using adjacency matrix K of I comma j to represent the length of a shortest path from I to j going through no vertex of index greater than k, we obtain the things will be calculated like this. A of I comma j is equal to minimum of k lies between 1 to n. K in the sense the calculation of the shortest path in the adjacency matrix. So this particular adjacency matrix will be iterated by adding the all possible shortest paths. So whenever you do this iteration, the first iteration is to be ak, that is k is equal to 0. That is what the adjacency matrix that you will obtain. Second iteration you will get a1, that is after somewhat little improved version of that. That is ak, that is a1. A2 means improved version of this previous one. Like that, these arrangements will be done. So to represent these adjacency matrix, we represent via k. So ak means k is between 0 to n. That means how many number of iterations you do. So ak minus 1 of I comma k plus ak minus 1 of k comma j comma cost of I comma j. So whatever is the minimum that you will select, that minimum cost will be added to the previous path. So this is what the way you will iterate the solution and will get the problem, get the best possible path. So finally, by adding these things, uh, see this is the one with no intermediate vertex. But if you want to go from one vertex to another vertex, you are supposed to pass through some intermediate vertex. So whenever you are supposed to pass through intermediate vertices, the solution will be like this. The formula will be like this: ak of I comma j is equal to minimum of ak minus 1 of I comma j comma ak minus 1 of I comma k plus ak minus 1 of k comma j. So where k is the intermediate vertex that you pass through. So here is the problem. Here is the solution for this. For I is equal to 1 to n and for j is equal to 1 to n, do. So add the cost, that is place the cost of I comma j in the adjacency matrix. For k is equal to 1 to n and for I is equal to 1 to n and for j is equal to 1 to n. If you want to go from I to j, you check for whether intermediate node is available or not, or intermediate vertex is available or not. So I to k and k to j, you are supposed to check it. So for this, a of I comma j is equal to minimum of a of 1 comma j comma a of I comma k plus a of k comma j. So since you are using 3 for loops here, the time complexity of this dynamic programming, that is all-pay shortest path algorithm solving using dynamic programming, is order of n cube. Let you consider this graph 1, 2, 3. Here this is a directed graph. 1 to 3 there exists a weight, and 3 to 1 there exists weight, and 2 to 1 there is a path and having corresponding weight, like that 1 to 2 and 2 to 3. So if you form a matrix, this is A naught. This is called A0. Here 1 to 1 is 0. There is no path, and 1 to 2 there is 4 is the weight. Like that 1 to 3 11 is the weight. Like that you fill the weight. If there is no path from 3 to 2, 3 to 2 there is no path. So you keep it as infinity. Now first you focus on the infinity. That will focus on the infinity. That means in order to go from 3 to 2, there is no path. You search for is there any other path available. Yes, there is a path. 3 to 1 and 1 to 2 is the path is there. So from the previous matrix, that is A naught, you check for 3 to 1. So 3 to 1, is there any path is there? Okay, 3 to 1 path is there. The weight is 3. So from 1 to the destination 2, is there any path available? Yes, there is a path. 1 to 2, there is a path with weight 4. So 3 plus 4 is 7. So that infinity will be replaced with 7. So since it is a minimization problem, so it is better than the previous state. That is, infinity is here and next one is 7. It is previously better than the previous one. So here principle of optimality holds. Whatever is the initial state may be, the next states must be better than the previous state. Obviously, the next state will be, that is next weight or what you have obtained is better than the previous state. Now take the, this is the AK, that means A1 matrix. Now you are supposed to improve this matrix. So how you will improve it? Now you will go for 1, 2, 3. So 1 to 3 is there any path available? 1 to 2 is there, 2 to 3 is there, and directly 1 to 3 is there. So if you go from 1 to 2, it is 4, 2 to 3, it is 6, 2, 4 plus 2 is 6. So previously, in the previous stage, it is 11 is there. It is better than the recently computed distance, that is 6. So replace 11 with 6. Like that, you check for any other possibility. So there is no possibility of adding this. This is what they call second matrix. Next, you improve it further. 1 to 1 we have checked, 1 to 2 we have checked, 1 to 3 we have checked. Now 2 to 1 you check it. So 2 to 1, if you go for 2 to 1 directly 6 is there. You can go from 2 to 3 and 3 to 1 also. So 2 to 3 is 2 and 3 to 1 is 3. So which is less than the previous one, 6. So you replace with 6 will be replaced with 5. Then we have visited all the vertices now. All pairs of vertices we have visited and there is no further vertex to visit. So thereby what will happen? This is the final solution and this is the final shortest path solution, that is all pair shortest path solution that you have achieved. So this is the way the dynamic programming works. So the best example of dynamic programming, the first example that we have seen under the graph category is all pairs shortest path algorithm. So it will work on the principle of optimality, that whatever is the initial state it may be, the next coming states must be better than the previous state.